Okay. Okay, so what I wanted to do today was give a little bit of an introduction to some work that we've been doing. Some of it's ongoing, looking at ancient New Zealand kauri. But I want to put a bit of a context on this first of all. This is a big program of work. Some of you might know Jonathan Palmer. No, that's not going to work. Who's with UNSW, Alan Hogg at Waikato, Pavla Fenwick, and at Gondwana Retrieving Laboratory, and many others. This is a really big program of work, so by all means, contact them if you know them. But if you want to find out more work about what we've been doing, we have a dedicated website, ancientkauriproject.com. And for work that has been published, a lot of it, you can find the links and download the papers from there as well. So let's put a bit of context on this. Why are we interested? Well, fundamentally, if you go back, just looking at observational records, one of the interests I have, particularly of using paleo, is actually getting a handle on the drivers and mechanisms of climate change and their impacts. And this is a lovely little animation from NASA, looking at the spatial trends, as best as we know it, of warming, cooling relative to the last 30 years over time. And you see in the 40s and 50s it got quite cool, and in the 60s starts ramping up and getting warmer. And one of the things you can see from this, and something that many of you will be familiar with from the paleo world, is actually what you get is as things start to warm up, the global average temperatures might not be much warmer than today, but at polar latitudes it gets very warm. This polar amplification effect, which we're starting to see today, this is phenomenal, the rate of change. Can we use the past for it? Because one of the issues we've got, of course, is the observational record is not where we're going to. The trajectory is off the scale compared to the last 150 years or so. So if we want to get a handle on where the future might lie, one thing is, of course, is using the climate models, but there's also the second one, is ground truthing, testing it with the paleo. And can we take particular periods in the past which might actually give us some insights into this? These are the sort of IPCC projections. You can see here in black is the trend in observational records with the uncertainties. That's basically a world average of what we just saw. And then the projections through depending on various different emission scenarios. And either way, we're up on where we are today. And we're already seeing quite dramatic changes. But like I said, that's all off the scale compared to the last 150 years. So the past is one potential way that we could get a handle on what might come in the future. This is from some of the Antarctic records, Dome C, I think this one is from, where you're looking at CO2 concentrations, basically fluctuating between 180, 280 parts per million, with a sort of beautiful 100,000-year cyclicity, and then below that the isotope temperature reconstruction paralleling that change. I won't go into that in detail, but suffice to say, we're now at 400 parts per million and going for it. We're rising up even further. So the question is, where are we going to go? Now, of course, whenever you do paleo, there's two fundamentals. It hasn't changed since I was a PhD student. It's chronology and climate. You've got to get a better handle on climate. We've got to get a better handle on chronology. And if we want to make paleo, I believe, relevant and really push it, we have to push the chronologies. One of the important issues here is how quickly things can move. Not in how much a rate of change might be in 1,000 years, but on decadal or even annual timescale. So we've really got to push the chronologies. And I think this is where the kauri is one particular angle that we can take. Problem is, if you say you're interested in dating, you'll probably get questions like this. One of my first books was on dating the past, and friends of my wife thought I was, if anyone knows me, I'm hopeless in this sort of thing, thought I was writing a book about dating, as in getting a couple, whatever takes your fancy, really. But regardless, that's not what you like. If you talk about dating the past, you might find stuff about dinosaurs. If you go specific and you look at carbon, you usually end up getting an image of a Turin shroud. It seems to be the thing that people associate with carbon dating. So quite a journey, depending on how you broach a subject of dating with the public. The key thing we want to use when we use chronology is we want to use nature. And with tree-ring dating in particular, it's one of the oldest dating techniques around. And this is an example. These are different examples of Tasmanian tree growth, where the fundamentals are that you actually have one ring following another. That actually dates back to Leonardo da Vinci, actually, back in the 16th century. He wrote this rather lovely piece. Rings and the branches of sawed trees show the number of years, and according to their thickness, the years which were more or less dry. Thus they reflect the individual worlds to which they belong. Beautifully written. In the north of Italy, they are much thicker than in the south. Fundamental point about how you can use tree rings and to infer chronology and climate. Just one of the many things this great man did. But chronology attracts all sorts, and really, much like Leonardo, polymaths were required. And if you don't know about Sir Charles Babbage, I really would encourage you to look him up. He's the father or grandfather of computing. He lived in basically the 19th century. He was a contemporary of Darwin. He was a bit of a sociopath. I think that's a fair thing to say. He was constantly, we've all got friends and colleagues like this, paranoid he was being ripped off and his ideas were being stolen. He hated poor people. He used to call them the mob. He used to worry about noise in London, and people would come and make terrible sounds outside his house, and he'd pay them to go away. It became quite well known for it. He once wrote a letter to the Times complaining about predicting how many broken windows in derelict warehouses there were around London. But he was a genius. And if you go to the Science Museum, you can see some evidence of that. This man, if he'd succeeded, we would be 6th, 7th generation computing. He created this thing called the difference engine, which basically did calculations. Think steampunk and some. This guy actually designed a computer using brass. It even had RAM. You would calculate the numbers, it would collect those numbers, it would then typeset it in theory and print it. And he was a perfectionist, which is one of the curses in science. He was a perfectionist. He never quite finished it. He took literally equivalent millions of dollars from the government in trying to do this. He only ever built small examples of it. Just a few years ago, the Science Museum built one part of his design to mark the centenary, or I think 150 years, I can't quite remember what it was, or 200 years. It worked. The bit worked. That actually he designed. You could have had brass computers that worked. It's an extraordinary thing. The problem was he was such a pain in the arse, and the government lost so much money, arguably he probably put computing back 100 years, because everyone just said, oh, Babbage had a go at that, it was a waste of time, which is a real shame. But you can see the movie footage of this. He had a terrible way of communicating with people. He wrote this rather wonderful letter to Alfred Lord Tennyson, the poet, and he said, in your otherwise beautiful poem, one verse reads, every moment dies a man, every moment one is born. And then he said, if this were true, the population of the world would be at a standstill. In truth, the rate of birth is slightly in excess of that of death. I would suggest in the next edition of your poem should read, every moment dies a man, every moment 1 and 1/16 is born. That's science communication. That is worst, I think, anyway. So the man was a genius, but he had issues. Let's just put it like that. But he was also fascinated by the idea of chronology. These guys were interested in everything. And he spotted the idea that you could use tree rings as a way of getting climate and chronology. And there's this lovely piece from an article he wrote in 1838. These preeminent effects are obvious to our senses, but every shower that falls, every change of temperature that occurs, and every wind that blows leaves on the vegetable world the traces of its passage, slight indeed and imperceptible perhaps to us, but not the less permanently recorded in the depths of those woody fabrics. So here he's talking about mid-19th century, he's talking about this. Incredible concepts. It took a lot longer for us to actually build on the ideas of Babbage, but we're there. Now, parallel to this, carbon dating was the key, because tree rings can only get you back so far. And tree rings, though, have been fundamental for how we actually use carbon dating. And it's primarily thanks to this extraordinary man, Willard Frank Libby, if you're not familiar with him, won the Nobel Prize for his discovery. He was on the Manhattan Project, and a series of papers in the late 40s demonstrated what you could do with radiocarbon dating. And there's various papers. This one was published in Science, Radiocarbon from Cosmic Radiation. Rather wonderfully, one of the principles was they realized that radiocarbon was being produced, or they thought, in the upper atmosphere. What they wanted to show was that modern living things had what they would expect, a level of radioactivity. And although it says biomethane, you can probably guess what that means. He went into the Baltimore sewage works and collected the methane from the sewage there and measured the C14. And thanks to the good people of Baltimore, it was demonstrated that radiocarbon activity is what they expected. So much so that a couple of years later in science, Libby and another colleague, Arnold, took a series of things of what they thought were known ages and then actually radiocarbon dated them and realized that on the rate of decay of what they expected, it basically fell in a straight line. And one of the key ones, the oldest ones, was a tree ring record that they had that was of known age, or what they thought was known age. So it was proved suddenly radiocarbon was real and it could be used. And something we'll come back to a little later, but because fundamentally it forms in the upper atmospheres where nitrogen captures another neutron and gets turned into radiocarbon. But you also can generate another isotope, which we'll come back to, called beryllium-10, which is in the ice cores. The key thing, though, for carbon, of course, is it cascades, well mixed in the atmosphere, you photosynthesize, and it fixes it in living material. And that's the fundamental premise of radiocarbon, as I'm sure many of you are familiar with. But the problem was that people realized that must change through time. And various people showed this. It doesn't come up very clearly on the plot here. This is from a paper back in Nature, using tree rings again, and showing actually radiocarbon ages do not equate to calendar years. They fluctuate because of changes in the carbon cycle, the amount of productivity in the upper atmosphere. So it fluctuates quite substantially. The key thing is now, this is the state of progress that we're at. This is INCAL 13, it's the International Calibration Curve record. It's radiocarbon dated of tree rings, absolutely, through to just into the end of the last ice age, which is the grey column on the far left-hand side of this right panel. And you can see the one-to-one curve. The C14 basically dips almost all the time below that curve. So if we want to actually try to convert our dates, our samples, our records of climate, we have to exploit this. This is actually good if we really want to push chronologies. We just need to put a lot of dates, a lot of money, and we can actually start picking up this variability, these fluctuations. Problem is, some of the biggest changes, the ones we really want to know, happened before the Holocene. So what are we going to do about that? Another thing we also have an issue with is the fact that actually if you look around the world, and particularly in the southern hemisphere, it's not all the same age. Things living today are not the same. This is some work from Edward Bard and others. It's a latitudinal transect, the Pacific and Indian Ocean in black, and the Atlantic in open circles. And effectively, in the mid to low latitudes, it's about 400 years radiocarbon offset in the surface ocean samples. And at high latitudes, it gets a lot older. And it's basically, and we'll need this figure a little later, it's basically even changes in the ocean circulation. The areas in yellow are where we get so-called deep water formation, cold, saline water sinking, drawing down carbon from the surface, which eventually upwells around the world, following the abyssal forming abyssal waters at the bottom of the oceans and welling up later on. So much so that by the time you're out in the higher latitudes of the Pacific, it could be 1,000+ years. That upwelling water tends to actually cause an offset in the southern hemisphere because of the greater amount of open water. And here's Jonathan. One of the things we're interested in is just the last few hundred years. Can you actually detect changes in how ocean circulation, how the southern hemisphere offset this difference competes? If you're getting older carbon welling up, arguably it would dilute the southern hemisphere. Traditionally, it's always thought to be about 35 years. So this is Jonathan coring some of the Dracophyllum trees we've been doing in the subantarctic islands. And on an Antarctic expedition, the AE for 2013-14, we actually took samples from Campbell Island at 52 degrees south. And we could get back a couple of hundred years with this, and we basically find it does vary through time. Okay. So actually periods when the red, which is the southern hemisphere average, and the northern hemisphere, which is the darker curve, actually almost converge, and other periods where it disappears. And if you're interested, you can go to the website spiritofmawson.com or go to the journal article. But basically, it does look like there is variability. It's not constant as well. So you've not just got changes globally, you've got changes hemispherically. So how do we get back further? And this is what we've been working on. We've been working on KAURI. It's a long-living tree. Just a show of hands, how many people have been over to see the KAURI in New Zealand? Many people seen it? A few of you. Okay. Have many of you seen much of the fossil stuff at all? No? Okay. Well, I've got some examples here just to show you what we're doing. They can live up to 2,000 years. We don't actually know. A lot of the ones, and I'll show you photos in a moment, were actually chopped down during early European settlement and harvested. But they can grow up to 30 meters in height, arguably even more than 5 meters in diameter. These trees are vast. And basically, they do lay down an annual tree ring each year. They form in the austral spring and summer, and they preserve also a climate signal. In fact, particularly, the modern trees seem to have a link to the tropical Pacific. So this is examples of them today. This is Tane Mahuta. It's the largest tree by volume. It's a bit bizarre, really. We describe the size of the trees basically on how much timber there is for felling. No one would fell this. It's not actually the largest diameter. It's 4.8 meters across the farther forest. If you've been to see KAURI, you've probably seen this majestic tree. It's near the road. Sometimes growing groves, but there's not many of them left, sadly. They were decimated when the Europeans came in. These are some examples of some of the shots. That's quite a small one on the left, but here's an example on the right where they're cutting them down. They're huge beasts. The KAURI trees as well, the young ones, grow incredibly straight and tall. So they're very popular for spars. You might not be able to make out, but this image here is two Royal Naval vessels. They're dragging tree trunk spars there for the ships. So they decimated the forests, the KAURI forests. They're growing them back now, but they're relatively slow living. But we're very fortunate. We actually have subfossil, what we call subfossil KAURI. These are trees which have grown thousands of years ago and then buried in peats. This is Jonathan here standing next to one of the KAURI. This is 55,000 years old. We dated this one. You can see the scale of him there. Some of the sites have even got, you can see the outline hopefully here, the base plate, the roots, and then the direction of a tree growing out. So this is basically where farms have been dug. They've had drainage ditches. The peat has collapsed, and as a result, they've dried out on the surface. And you can see the outline. So someone's come along and just drawn an outline of the tree on the surface. And the guys are digging those out. It's very hard, if not impossible, to touch living KAURI. But the ancient material you can harvest, and it's a relatively poor part of the country, but the timber yards have been brilliant with us, and we're working with them. That each tree they harvest, they'll give us what we call a biscuit, a slice of a tree. We give them a date, and they'll turn it into material to working. I brought an example along here. Just pass it around if people are interested. This is what we call Finlayson 6. It's about 10,000 years old. The glue is not obviously 10,000 years old, but just to give you an idea of what the rings look like. So if I could just, I'll start at this end if that's all right, and pass this round. Just feel free to pass it round. But what they do is they're turning into all sorts of things. Bowls are quite popular. This is a 50,000-year-old bowl, fruit bowl, so have a look at that one. Bathtubs are very popular, apparently. You imagine the root plate cut, you carve it out, cover it in resin, and then you can bathe in it. So you have a 50,000 or however old bathtub. They're not cheap, they're about $30,000, $40,000. Even to the extreme of pate knives. This is a 50,000-year-old pate knife. So have a look at that. It's beautiful material. The weird thing is, it looks like it was chopped down yesterday. It's not rotten or gnarled. Sometimes on these surfaces of the bogs, what you'll find is that it'll often have the top half of the trunk will be rotten because it's been exposed to the surface. But that's okay. We just want the middle going out so we can get the bottom part. So that's okay. Hopefully this will work. So this is one of the guys demonstrating digging out one of the KAURI trees. near the surface. That is not charged. Extraordinary endeavour, huge amount of work and effort. And basically the wood is turned into bathtubs, pate knives, tables, thousands and thousands of dollars, and then sold around the world. So very, very popular, but beautiful resource. So what we're interested in is actually taking some of these kauri trees, and can we look at them for particular periods of time where we might actually get some insight. I'm not claiming by any means that this is the final, a major solution for all our problems with regards to past climate, environmental change, impacts, but I'm going to show 3 examples of some of the kauri that we've got. We've only done preliminary stuff, and we're going to do hopefully a lot more ARC willing, where we're actually trying to get a handle on what's happening. And we've chosen 3 particular periods here. One at the last termination, or the last glacial interglacial transition, which is, for those familiar, Antarctic cold reversal, younger dryas, basically last sort of 14 to 11,000 years ago. Just at the beginning of the last ice age proper, around a period that we call Heinrich 3, which we'll have a look at as well, about 28 to 32,000 years ago. And also another period, which is a lot older, about 40, 45,000 years ago, around something known as the LYNCH'S excursion. Each of those periods has particular features that we're interested in. The last termination on the far left is one where you've got this extraordinary asynchrony between the north and the south. We've got cooling in the north and warming in the south and vice versa. In the beginning of the last ice age, for what we're interested in here around Heinrich 3, you've got extraordinary big changes where you've got massive releases of ice into the North Atlantic and extinctions in Europe. And then around the LYNCH'S period, you've got also human arrival in Australia, arguably the same time in Europe, and we'll have a look at that, and also this whole issue about megafaunal extinction. And the question we've got is, can we use a kauri as almost like a Rosetta Stone, as a way of actually linking what the tree rings are doing with what actually is happening in the ice and in the oceans? Can we put everything together? This is something that Alan Cooper and I are putting the big grant application together. But one of the really interesting things is, although it's not necessarily warmer than today, what you're seeing is some of these periods, these abrupt warmings, are up to 16 degrees centigrade in just a few decades. It doesn't get much more extreme than that. So can we actually tie all this together? Because at the moment, we can't. The uncertainties of chronology are just too difficult. And one of the big challenges we've got is when you're actually putting ice cores together, when you want to link a Greenland to an Antarctic ice core, one of the primary ways it's done is actually using gas changes in carbon dioxide and methane, big fluctuations that happen and preserved in the ice, and then linking the patterns together. And the problem, the challenge it's always been, is the fact that as the snow falls and turns into ice, and we're compressed, is it takes some time before these gas bubbles are basically isolated from the atmosphere. And they're often offset quite a bit by up to several hundred years with what's going on actually at the same level at which climate is preserved in the ice. So you've got this uncertainty straight away of how you actually link Greenland to Antarctica. So can we use a kauri, and can we bring the mid-latitudes, the low latitudes where people live, into what's happening in the climate record preserved in the ice? We've been developing now, with Jonathan in particular, has been developing a series of really old chronologies all across Northland in New Zealand. There's about 20 of them or so now. They're all in yellow here. The late Holocene, which is a more historical master chronology, is in grey. And so we've been looking at this ancient kauri. We've now got more than 20 bog sites. They span everywhere from the early Holocene back to 60,000. Finlayson's one of the early Holocene trees, one of the wood that's just coming around at the moment. And what we can do from that is this is KAURI tree rings. What you can do is you can use the thickness of the tree rings, just as Leonardo or Babbage suggested, as a handle on climate, but also because you can actually measure what's the amount of radiocarbon preserved in the same rings, you can actually get a handle not just on what the radiocarbon calibration curve is potentially doing, but also what's happening to carbon dynamics. And typically, rings are on average about 1 to 1.7 millimeters, just over 1 millimeter in thickness. So they're not large, as you'll see when you have a look at the wood. So this is an example. This is the Greenland core you just saw before, but this is going from 25,000 to 50,000. Big swings in climate, several, as we've heard, 16 degrees or so. Changes just on those abrupt warming events. And we've got multiple trees now, or series of trees that overlap that actually look like they coincide with these periods. And I'll show you how we're just doing this at the moment. If you're interested, there's a paper 2015 that Jonathan headed up, pulling these trees together. These were only just preliminary dated. What we want to do is really interrogate them further. So this is one example. Let's have a look at what we can do with just some basic stuff that we've got already. And one of the things that's always been curious is about the timing of modern human arrival in Europe. The so-called Cro-Magnon man. So this is an example of Cro-Magnon man. If you're not familiar, you can actually there's actually a company called Bones of Us. You can get actual casts. This isn't a real one. A few years ago, I took my grandmother, when she was alive, bless her, to the Edinburgh Science Festival, and we packed these into the hold, and we got through, and bless her, Nan was 90 at the time, and we got through security, and then we're just waiting around for the plane. Now, there was a call for Dr. Turney. Would Dr. Turney please come to security? And basically, we worked our way through all these business folks, and this lady, who looked absolutely grey and gaunt, looked, and she said, are you Dr. Turney? And I said, yes. And she said, would you like to declare anything? And I realised straight away, oh my God, was she seen in the thing? And I said, oh, you don't need to worry about it. They're just plastic. And the look of relief on their face absolutely fell. And she phoned through and said, it's all right. They're fine. They're only plastic. And she looked at me like I was a homicidal axe-wielding maniac. And the awesome thing was, they didn't check. So if you are a homicidal axe-wielding maniac, just go for it. Say they're plastic. So this is Cro-Magnon man. We've all hopefully looked very similar to this with mandible and the like, but basically just over 1 litre in brain volume, very straight face. Classic features. In contrast, of course, we have the Neanderthals. I mean, huge differences in volume of brain, highly variable, about 1.2 litres, very sloping face. Far better teeth in this example. They pronounce eyebrow ridges as well. And so this question mark about actually, if people want to wonder it, yeah, have a look. This question about what happened to the two has mystified people for a long time. And this argument, I mean, when you discover a new species of human, if most of you in the field, you know, it's hugely controversial. When the first Neanderthals were discovered, people couldn't believe it was another species. In fact, one of the first ideas was it was a Mongolian Cossack who got lost chasing Napoleon back from Moscow in 1815. So all sorts of crazy ideas come around when you discover a new species. So there's been some really exciting work done from Oxford, where what they've done is they've carbon dated using a method called ultrafiltration, which removes a lot of contamination of human remains, modern human remains, and also Neanderthals. Kent's Cavern in the UK, they haven't got a remaining date anymore, unfortunately, because there's no material left that's appropriate, but they're coming in at ages just above 37,200 radiocarbon years. And as we heard earlier, that doesn't equal 37,200 calendar years, so you've got to convert it. Oesi, I'm sure I'm pronouncing that incorrectly, but in Romania is arguably some of the earliest evidence. It's actually slightly younger, at 35,000 radiocarbon years, and that's a picture of it just there. And then subsequently also, late Neanderthal looks like around the same sort of time, arguably maybe a bit before. Spy is one of the latest founds of Spee, is that is pronounced, Spee? Spee in Belgium at 35.6. So they're all around the same sort of time. And when you use INTCAL, which is the standard of using all these other ways of calibrating records, you get age distributions much like what you see the grey column here. And the key thing just to note, and just keep your eye on this, is if you look on the blue curve above, which is Greenland, effectively the age of this early human at Kent's Cavern, 37,200, just looks like it basically comes in at what they call interstadial 11. So that's giving you some sort of climatic context. What we're saying is it looks like around interstadial 11, the peak in oxygen isotopes when it's warmer, or possibly just for very cooling at the end, it looks like that's when modern humans got into Britain at least. So that's based on the calibration. One of the things we've been working on, though, is we've got several trees from a site called Mangawai which cross-date with one another. So you have a pattern of a tree ring growth, just like Leonardo and Charles Babbage show, actually compare really well. So we can actually really be confident in the chronology. And then we've done dating on these. Now, the key thing here, this is a pattern of C14. It's a 1,350-year sequence of radiocarbon ages. Just note that the ages range from about 41,000 at the inside of the tree series down to about 38.5, give or take. Now, the crucial thing is, if you remember that plot I showed earlier, when you create C14, you also create beryllium-10 in the upper atmosphere. And that'll often snow out and be trapped into the ice cores. They're effectively being created at the same time. So peaks in beryllium-10 coincide with same changes in C14. And working with people like Raymond Muschler, this is a paper that came out in 2014 using a series, is actually what you can do is you can convert those changes in beryllium-10 in the ice cores, which is these peaks here in the red and the black on the second panel. You can convert those to radiocarbon changes effectively. You can put it through a model and you can convert the output. The key thing here is this is that series basically put on the same trend. And basically, here's the KAURI C14 and here's a beryllium-10 generating another radiocarbon record. The panel C is from the ice cores, panel D is from the tree. So we can lock in and then actually we have a calibration series, albeit a 1,400-year one, locked onto the Greenland ice core. So it's a way of aligning the two records. We're very fortunate this particular period aligns with something what's known as the Le Champ geomagnetic excursion, where things went extreme, very big. So we can actually pick up the structure of that and then link the KAURI that you're seeing against the ice cores. The key thing is, Kent's Cavern, which is one example, is the oldest date we have, somewhere around that mark, let's say 37,200. It's too young relative to Mangawai. It doesn't fit. It's younger than Mangawai. So the practical upshot of which is, this is where you would have placed Kent's Cavern, using the calibration curve as we understand it. Now, it must be, based on where we fit the Mangawai, it must be somewhere in there or younger still. We don't know. So it changes the context of where the modern humans and the Neanderthals, which were after that, the climatic context. So just by using a KAURI, we can actually say that placement's not right. It could be later. It could be a lot later. We just don't know. If we come through to the abrupt climate changes that we've been hearing about before, these abrupt warmings, in the blue here, this is from the West Antarctic ice sheet record, the oxygen isotopes from Greenland in blue in the top panel, and then the Antarctica in the yellow and purple. You see this there seems to be this sort of antiphase relationship. The warming in the north leads to cooling in the south, or vice versa. We're not quite sure. The H numbers, H6, 5, 4, and 3, in this one here, are what we call Heinrich events, these big discharges, massive collapses of what we think is North American and possibly European ice into the North Atlantic. Linking that to the ice cores is problematic in itself, and then tying that to the southern hemisphere even more so. Some work has been done in the Southern Ocean, and we do have evidence for other ice rafted debris events like Heinrich events in the South Atlantic, and Camfush and others have shown this, what we call SA 0 to 5, the bottom panel there. So you get peaks in the ocean sediments which look like they're Heinrich-like events, but they're happening at different times, as far as we can tell. So the implication is that the Greenland and Antarctic ice sheets have are operating on different timescales. And basically, since I've been a PhD student, one of the paradigms that we've had to explain this sort of apparent antiphase relationship is this thing called the bipolar seesaw. And the bipolar seesaw is the concept that cooling in the North Atlantic leads to a collection of warmth and increased heat flux to the southern hemisphere. And eventually then it suddenly switches and it goes back to the northern hemisphere. So you have this antiphase temperature relationship, just like a seesaw between the two. And one way of thinking about this, or one of the classic mechanisms, is through the ocean, the idea being you shut down deep water formation in the North Atlantic, and you basically increase upwelling and processes in the southern hemisphere and vice versa. So it's out of kilter. That's been one of the ways. Somehow the Atlantic meridional overturning circulation is going backwards and forwards. That's been the paradigm. And effectively, at one level, that fits with what the data is. But the problem is we've got big age uncertainties. So let's have a look at two examples. I'm a bit aware of time now with the delay. But let's just have a look at one, the end of the last ice age, the last termination, what some people know as the last glacial interglacial transition. Commonly, people might use the term the younger Dryas, or Dryas octopetala. It was first identified by basically daisy pollen. If you're familiar with James Lovelock's wonderful stuff on Gaia, daisy world, basically daisy world existed in Europe during the younger Dryas. It was very common. A period of what looks like cooling, which is typically defined as somewhere between 11,500 years to 12.7. Depends on who you talk to, what records you're looking at. This is the Greenland record in blue at the top. This is from the Waste Divide record. And what you appear to have, based on those gas links with Antarctica, is warming in the southern hemisphere based on Antarctica. So you appear to have this cooling in the north, warming in the south. And the cooling in the south is called the Antarctic gold reversal. So that sort of fits quite well. It looks like that's consistent with the idea that the North Atlantic shuts down, possibly because of fresh water pulse in the North Atlantic, shuts down deep water formation in the North Atlantic, and then it warms in the southern hemisphere, and arguably almost synchronously. So one of the things we wanted to do was actually test this as an idea. And one of the things we've been very fortunate with, we have a site called TOWI. This has just been published in Scientific Reports. It's a 1,500-year, or just shy of 1,500-year sequence. We've got close to 40 trees cross-dating. It just stumbled across it. We're very lucky. It was a terrible drought. Lots of trees were discovered. And the result is all these trees cross-date beautifully. So we've got this nearly 1,500-year record. The practical upshot of which is we have done decadal blocks with Alan Hogg and John Salvin, decadal blocks of C14 going across these trees. So you have this continuous record of radiocarbon. The great thing is we've got enough C14 that we can lock it in to the end of or the beginning of the Incal tree ring record. So you've actually got one on top of the other, so we can lock in all the way and extend back. And that allows you to start playing with some ideas, because what it basically allows you to do is we've got an absolute chronology within plus or minus 10 years that extends all the way through annually resolved. The ice cores have got various dating issues. They're brilliant, but there's dating uncertainty. But can we actually then compare them? We're very fortunate that actually there's another record called Kariako Basin. And Kariako Basin is a marine record. It's marine sediments in the tropical Pacific. And effectively, if you look here at this panel here, what's panel E, the blue is the radiocarbon ages in the surface waters of Kariako Basin. And that looks like almost most of the time, Kariako Basin is behaving itself. The forams that live in those surface waters are basically reflecting atmospheric radiocarbon levels with an offset of about 400 years. That ocean upwelling of old carbon has an offset of just over 400 years. When you put on the KAURI and we link all the European trees together, what I hope you can see is there's two grey columns there. And those are periods at which the blue curve, the Kariako Basin surface waters, diverges from the trees, or the atmospheric C14. So what that's telling you is there's two periods when the oceans are doing something different at Kariako to the atmosphere. Most of the time they just map on really beautifully, but there's two periods. And the first one is this massive divergence that starts about 12,900 years ago. And one of the arguments seems to be that actually that massive collapse in C14 age, the divergence, is a result of the Atlantic shutting down. Basically, you get stratification of the surface waters, you're no longer getting an upwelling of old carbon, and the surface waters now just reflect truly the atmospheric C14. So up before, it was following 400 years, now it's just collapsed, with a second pulse here in the mid-Younger Dryas. What this seems to show is that actually during this period of cooling in Europe, you get two phases where the Atlantic circulation system looks like it just shut down, just completely shut down. But the rest of the time, it seems to have recovered. They fall in line on top of each other beautifully. The Cariaco Basin is an annually laminated record for this part of the series, and Conrad Huon's original work looks like it's bang on. So it actually looks like you can actually align an ocean record with a terrestrial record and actually get insights in what's happening in the North Atlantic. What's extraordinary about that is the fact that we've still got a cold period. Europe was still cold through that event. And the traditional view is it would have just been because the whole deep water formation had shut down. If you look more closely and zoom in at the beginning of this change, this in the blue is the shift in the trade winds over Cariaco Basin. And basically, when that change, when that collapse in the ocean C14 record happens, is when those trade winds shift south. So that's consistent with that idea of cooling. But it's, the wind stays south after that event, and yet the C14 is still turning over. What we think might be happening is the ocean circulation system, the deep water formation, is happening, but it's happening further south. And actually, it looks like what we think is happening is at the polar front, the sea ice extending across the North Atlantic was a lot more extensive. And effectively, Europe was just in those frigid polar waters. What's fascinating is that about 12.6 thousand years ago, just when the Cariaco Basin is saying the winds are further south, you suddenly get this amazing shift. The green curve just here on the top right is the difference between the trees growing in Europe and those in the KAURI. And looking at the C14. Most on the left-hand side, it's about 35 years. That's what we get today. We get an interhemispheric offset, the northern hemisphere, southern hemisphere, about 35 years. But before 12,600, 700 years ago, it was close to zero. It basically said the north and the south was the same age. That's a huge difference. And one of the things we're suggesting, actually, is at that point at which it triggers, which is when the winds were furthest south, maybe that's the point at which sea ice in the southern hemisphere just collapses and releases all this old carbon, which has been sustained ever since. Before that point, sea ice in the Southern Ocean, we think, maybe was capping it. So here's a way of actually linking in. And although the ice cores are saying, oh, the Antarctic cold reversal ended here, we're saying against the climate record, it's a bit later. It's after the Younger Dryas has well and truly started. And just very quickly, just to go even further back, well, let's test that even further. Let's see if we can actually have a look at a Heinrich event, one of the big events, one of the things that actually supposedly is something that drives bipolar seesaw. If you put a vast amount of fresh water in the Northern Hemisphere, or North Atlantic, the argument is all that fresh water will cap it, will stop deep water formation, and then you'll get a bipolar seesaw response with a warming happening in the south. The problem is, been a number of great papers. Stephen Barker from Cardiff had a paper in Nature just last year, and then Jean Lynch-Stieglitz had a great paper in Nature Geoscience in 2014, showing actually ocean circulation wasn't really doing much for this period. Wasn't doing much. In fact, ever since I've been a PhD student, really, Bond and Lottie had a paper back in '95 saying it didn't look like it was right, and everyone chose to ignore it. But there's been more work since. It doesn't look like the Atlantic was massively overturning the whole time. There's a wealth of papers. The problem we've got, though, is we've got this anti-phase temperature response between the north and south. So if it's not being shut down by the ocean, what's driving it? And we're very lucky. We've got one tree, a Finlayson, another Finlayson tree, which is 2,000 years long. It's about 29,000 years old, and we've done every 20 years C14 all the way through. And we can wiggle match that pattern of C14 against different records of radiocarbon. They're not so well resolved, but Cariaco Basin, which we heard about, or Lake Segetsu, the chronologies are different in absolute time, but you can pick out the structure, you can pick out the inflections in the C14, which means you can lock your tree ring record into those series. You can get real detail where they count. And following the same principle of what we were just talking about using a beryllium 10, we can compare the Finlayson tree, the C14 pattern, with what's happening in the ice cores. And with Raymond Muschler and Florian Adolphi, actually, the green from the tree is the C14 compared to the C14 from the ice cores generated from a beryllium. And you get this age solution, which shows that you've got this period in here where the trees fit. It's the only solution we can get. So we've got a conundrum. We've got an issue where we've got antiphase temperature trends in the northern southern hemisphere, and then you haven't got a bipolar seesaw. So can you do something a bit different? Is there another mechanism by which you can drive this global change? And one thing, as many of you know, we've been working with Peter Kershaw and others for a while now on LYNCH'S crater in tropical Queensland. It's a miserable 2 weeks we had there. It was like the Western Front. There was mud everywhere. 64 metres worth of sediments down to the base. And we wanted to take a record that spanned the same period of time as that KAURI. This panel in the middle, LYNCH'S crater, panel C, we took 45 radiocarbon dates for a 1.5 metre section, 45, and then overlaid that onto the KAURI. And the practical upshot of which is that when you do that, you can calculate how much, you get a measure of how dry the conditions were. And effectively, there's a dip. It looks like there's a drying happening in LYNCH'S crater at precisely the same time it's cooling in the ice cores in Antarctica and warming in the north. So what do we look like we've got are synchronous changes in tropical Queensland to Antarctica and the North Atlantic. And just quickly summarise, if you're not getting it by an antiphase relationship driven by the north, maybe one of these Antarctic ice-rafted debris events is the cause instead. If you've got it cooling in Antarctica, if it's not the north driving it, maybe it's the south. Working with Stephen Phipps, what we've done is we've tried that. We've done something comparable to what's known as the Meltwater Pulse 1A, and we put a freshwater dose in the Ross and Weddell Seas. Panel B, which is this one here, over 300 years, what it shows is that tropical Queensland, extending out into the Pacific, gets drier as a result of that freshwater hosing, fitting with the LYNCH'S crater data. So what it looks like is what we might have is actually evidence on the ground showing that you can actually get that response in the Pacific. And if you notice on the far left-hand side, we get a warming in the North Atlantic at the same time. It looks like there's an atmospheric teleconnection. This is what we're just putting in prep. So just to wrap up, sorry, I'm acutely aware we're running over, aren't we? So the KAURI trees are a way that we're using it. We're using a C14 to lock things together. It allows us to push chronologies at a point at which we've never been able to do my group before, which we're really excited about, and it allows us to test hypotheses, be it not just climatically, but biologically. And if all else fails, keep calm and use the past. Thank you very much.